This is for Year 12 methods. It's an explanation of 4F for VCAA 2011 Exam 2 question number 4. In question number 3, you're asked to give the value of K such that Tasmania would directly run from the camp to the point 10. So here is the camp, and he's running directly here to 10. So in this particular case, you would want to take the derivative of t with respect to x, make it equal to 0, given that x equals 1, and solve for k. And that gave you k equaled 1/4. And that's running directly here and then swimming up the river. In part F, so in question F, they're saying you should run directly from the camp to the deceleration plant. So in part F, we're running from here directly to here, and this is the value of x, √7/2. Now you'll notice that if the time for the run plus the time for the swim, if you make x equal to √7/2, √7/2 squared is 7/4, the 4's cancel, 7 minus 7 is 0. So it actually equals 0. So it really is only the time of the run. I know that if I made dt dx equals 0, and I make x equal to √7/2, that the value of k that I get is 5√37/74. And if I was to look at that, so I open up a graph, I take this, I've set k equal to 5√37/74, and I get a graph that looks like that. So this is time against x, and you've obviously got a point here where it is the minimum amount of time, and then it starts going up again. And if I was to put that x equals √7/2 on the graph, there it is there. That's the point at which when k equals 5√37/74, the minimum time exists. Now, the question at hand isn't really a derivative equals 0 question, because it's asking for the minimum time. That's true. However, the minimum time will happen only once. It will happen when k equals that particular value. But what it's asking is, what are the other values of k that mean x equals √7/2 is the shortest time to do the run? So I'd like to explore what the graph looks like for different values of k. So this is where k equals 0.41, and that's this particular graph. So if I make k equal to 0.1, that is less, I get that graph. And because I pressed XC, I lost my previous graph, so I'll put that on. Now, 0.1 is no good because I can see a minimum time here, and I actually want this here to be the minimum time. So let's try 0.3. Now I'm trying 0.3 because I know that my actual answer is 0.41, and I can see a minimum time about here. If I make 0.41, I should actually get a time that gets less. It's minimum here, then it starts to increase again. Because I know that when I take the derivative, which is what I did up here, I took the derivative. Okay, you redraw them. I'll just wait. Finished now? Okay. When I take my derivative up here, and I get this particular value. So if I was to consider 0.5, now you'll notice that the time is high, it gets less, and the minimum time for all of the times, if x equals √7/2, is when x equals √7/2. And if I make k bigger than that, so 0.6, I get a graph that decreases. Now, this question isn't asking for the derivative equaling 0 local minimum. It's just saying, given that I'm going to run straight to the desalination plant, I want to make when x equals root 7 on 2 the smallest time. And given all the values of k shown here, it's only k values equal to or bigger than this that actually give times where the smallest time is root 7 on 2. So in actual fact, in this question, what I'd like to be doing is I'd like the gradient to be negative when x equals root 7 on 2. So the gradient is equal to or less than 0. Why do I want it to be less than 0? I want it to have a negative gradient, because if it has a negative gradient, it means that over here it will have the smallest time. So I want, for fear of losing my graphs, I want this is my answer for k, because they're the answers of k that have gradients that are negative, or when it's equal to this value, 0, and that means that root 7 on 2 has the smallest time for all of the values of k. So that's what I want to do.